This is Grand Admiral Rosine, following the physics directive to explain conceptual modern physics. In this video, we will explore the quantization of energy. From quantum mechanics to quantum field theory, the quantization of energy is among the most important discoveries in modern physics. The mathematical idea behind it was first proposed by Max Planck as a solution to the ultraviolet catastrophe. The ultraviolet catastrophe was a problem with the classical interpretation of black bodies. Black bodies are idealized objects that are perfectly black, meaning that they don't reflect any energy, but absorb it all. If they are in a vacuum, which has zero energy, so no temperature, that absorbed energy must be emitted into the vacuum. It will be emitted as electromagnetic radiation, which is just light. Classical energy predicts low-frequency emissions very accurately, but when frequency gets high enough, therefore being ultraviolet, it predicts that the energy emissions will approach infinity. With infinite possible frequencies, infinite energy should be emitted. While stars aren't black bodies, their energy emissions can be calculated similarly. As a result, classical energy fails to match our observations. It predicts that stars, like the sun, should emit infinite ultraviolet radiation. Max Planck was able to explain this by saying that electromagnetic energy couldn't be calculated as though it were infinite. Before, it was believed that you could split energy infinitely and always get smaller fragments. But Planck proposed that energy would eventually reach a point where it could no longer be split, separating it into discrete packets of minimum energy. The amount of energy in each packet was higher the higher the frequency of that light was. Under this assumption, the ultraviolet catastrophe was now solved. As frequency increases, the energy in a single packet will exceed the amount of energy available to spend, preventing that frequency from being emitted. Likewise, even at the highest frequencies that are emitted, less energy will be emitted since there will be a missing packet holding a significant amount of energy. But this only solved the problem mathematically. Energy was still believed to be infinite. That is, until Einstein explained the photoelectric effect. Take an atom with a beam of light shooting at it. As the light is absorbed by the atom, it gives the electrons energy. According to classical physics, no matter how low the frequency of the light was, if you shot a beam with a high enough intensity, which is a measure of how much light is being fired at it, it should provide enough energy to dislodge an electron. But experimentally, this does not happen. In fact, the intensity doesn't matter at all. The only way to dislodge an electron is to fire a beam with a high enough frequency. Einstein explained this by proposing that light is not only quantized mathematically, but actually consists of particles, which are now called photons. Photons are not particles as one usually thinks of them, but merely packets of energy. They have no mass, and therefore can travel at the speed of light, which makes sense since they are light. And they also take up zero space. They are simply points of electromagnetic energy. This will be explained better in future videos with quantum field theory. Because of this, intensity only increases the amount of photons fired per second. The photons need to have enough energy, therefore be a high enough frequency, in order to exceed the potential energy keeping the electrons in place. In the next video, we will go deeper into the craziness of quantum mechanics. If you enjoyed this video, please give it a like. If you wish to further explore conceptual modern physics, subscribe to my channel and join me in the Physics Directive. Long live the Empire.